Hi, welcome back. In the previous lecture, we saw where the Navier-Stokes equation comes from, and we derived all the terms needed to write it in its full vector form. So this vector form will allow us to write the momentum equation in the three coordinate directions. In other words, we will project the Navier-Stokes equation along the x, y, and z axis. So in this lecture, let's move on to the conservation of mass. We keep the same configuration of fluid element of volume delta V. Delta V equals delta X times delta Y delta Z. And the mass of the fluid element is given by delta M, which is rho times delta V, and V, the velocity field of the fluid. So these three components of V, these three velocities can vary in space, which will cause the element to stretch or compress. This is delta Y, delta Y, delta X, and this is delta Z. Y, Z, X. So, what does conservation of mass mean? So, conservation of mass simply means mass cannot be created or destroyed. So, whatever mass enters a control volume must either leave it or accumulate inside it. In other words, the material derivative of mass is zero. So we can write d delta m over dt equals 0. So d delta m is also d delta m over dt. This expression is also d rho delta v over dt, which is, by using the product rule, we get delta v times d rho over dt plus rho times d delta v over dt. Over dt. So now let's compute the material derivative of the density and the material derivative of the volume. So d rho over dt equals the local derivative plus the convective term. So partial rho over partial t plus v dot nabla v dot nabla rho. Dot nabla rho. So now let's compute let's compute material derivative of the volume. d delta v over dt equals d delta x delta y delta z over dt. So by using the product rule, we get delta y delta z times d delta x over dt plus delta x times delta z times d delta y over dt plus delta x delta y d delta z over dt So let's now derive how each side length of the fluid element changes with time. So variation along y, variation along y. So the left face of the element, is at y, moving at velocity vy, and the right face of the element, is at y plus delta y, moving at velocity vy plus delta y, So now I'd like to draw your attention to this point, because the two faces move at different velocities. The length delta y changes over time. So the rate of change of delta y is simply the difference between the velocities of the left and the right faces. So we can write d delta y over dt equals v y plus delta y minus v y. So now we're going to expand the velocity at y plus delta y using a first order Taylor expansion. So v y plus delta y equals vy plus partial v over partial y times delta y. So when we subtract vy in this expression, we get d delta y over dt equals, instead of writing vy plus delta y, we use this expression vy plus partial v over partial y times delta y minus this velocity vy. So then we have d delta y over dt equals partial v over partial y times delta y. Similarly, in the x and z directions, we can write d delta x over dt equals partial u over partial y times delta x, d delta z over dt equals, over dt equals partial w over partial z times delta z. So let's now substitute the three derivatives we just found in the material derivative of the volume. So d delta v over dt equals delta y delta z. We substitute with the derivative just found, partial u over partial x times delta x plus delta x times delta z times partial v over partial y, delta y, plus delta x times delta y, partial w over partial z times delta z. So this is the volume delta v. This is the volume delta v. So this expression equals delta v partial u over partial x plus plus partial v over partial y plus partial w over partial z. And this is the divergence of the velocity. So this is the divergence of the velocity, nabla dat v. So d delta v over dt equals delta v times the divergence of the velocity. So let's now combine the two material derivatives. So d delta m over dt equals delta v times d rho over dt plus rho d delta v over dt, which is 0. So we replace the material derivative of the density by its derivative. Delta v partial rho over partial t plus v that nabla rho plus rho times the divergence of the velocity. nabla that v was 0. There is delta v here. Sorry, so this is rho times delta v, which is 0. So we can simplify by delta v. Then we get partial rho over partial t plus v that nabla rho plus rho nabla that v was 0. So by using the vector identity, we get partial rho over partial t plus nabla at rho v 0. So this is the conservative Eulerian form of the continuity equation for compressible flows. This is the continuity equation for compressible flows. Continuity equation. Continuity equation for compressible flows. So for incompressible fluid, rho is constant. The density is constant. The density is constant. That means d rho over dt equals 0. So from this line we can write partial rho over partial t plus v that nabla rho. So this expression is this is d rho over dt plus rho nabla that v equals 0. So this expression goes to 0. This is rho. So then we have rho equals 0, then equals 0. So this is the continuity equation for incompressible flow. Continuity equation for a compressible flow. Nabla that v. Okay, so